Thank you very much. Yeah, does it work? Yeah. Okay, so the plan today, it's going to be a hot day. So the plan today is to do dynamical degrees for birational surface maps. Discuss the theory on how to compute dynamical degrees of, let's say, an element of the two-dimensional Cremona group. And then I'll discuss a general construction of dynamical degrees in any dimension. Any dimension over any projective variety. Okay, and so what we're going to learn is that it's going to be very much connected to, so F, remember it's my dynamical system, my favorite or your favorite dominant rational map on some smooth, complex projective variety X. And we're going to see how it acts on the cohomology of, let's say, Durham cohomology of X. And then we're going to see that the dynamical degrees are directly connected to these actions. And to understand this connection, we will need to exploit the intersection form of the cohomology and positivity properties. The positivity here is going to be very much connected to positivity of line bundles. Okay, so these are the main, let's say, characters of the day. Okay, so let me start with the Cremona group. Apparently, you know what this is, so I don't have to redefine this. So let me pick F inside the Cremona group of dimension 2, which is to say over C. Sorry, I want to be perfect, so it has to be a perfect field. So I'm taking a birational map from P2 to itself. I remember that you define the dynamical degree by looking at the degree of the iterates of Fn. That was a submultiplicative sequence, so that the infimum of this is also a limit, and which is the first dynamical degree of F. Okay, so which is a number between 1 and plus infinity excluded. Okay, so the theorem that we'd like to show is this, is that in fact this number is very special. So lambda 1 of F is an algebraic integer. Okay, and even more precisely, all its conjugates. So lambda 1 of F is between 1 and plus infinity when I'm saying all its, okay, it's Galois conjugates over Q bar lies in the unit disk. In the closed unit disk. So when I'm saying all its Galois conjugates, of course, it's all the Galois conjugates except lambda 1. Okay. Okay, so these numbers are very special. So the picture is like this. So lambda 1 is here. Of course, lambda 1 could be equal to 1, but let's assume that lambda 1 is not equal to 1. So this is supposedly the closed unit disk, so 0, radius 1. And so you have two cases. So either the Galois conjugates are all inside the open unit disk. So let's say this is lambda 1 minus lambda 1 and inside the open unit disk. And so then this number is called Piso Vijayaraghavan number. So this is just number. In the literature, of course, they don't use this. It's just PV number. Okay. Then you have a second case where maybe, so for instance, if lambda 1 is a quadratic integer, then its conjugate is 1 over lambda 1. Okay. So it's a piezo Vajrayana. And then maybe you have one of the conjugates that is on the unit circle. So if lambda 1 admits 1 conjugates on the unit circle, then in fact, so you can play around, and what you show is that the minimal polynomial of lambda 1 is in fact reciprocal. So what it implies is that the reciprocal means that P, so if P is the minimal polynomial of lambda 1, so let's say with integral coefficient, so since it's an algebraic integer, its dominant term is equal to 1. And since it has 1 conjugate on the unit circle, then when you look at P1 over x times x to the d, the degree of the polynomial, then it also vanish on that point. And so this is equal to P of x. Okay, so what this says, what it implies, is in fact the conjugates of lambda 1. These are lambda 1. So lambda 1, 1 over lambda 1, and then all the rest are inside the unit circle. So in the other case, you have a situation like this, and then you have 1 over lambda 1. In this case, so when you're in the second case, you're called a Salem number. Okay, so the theorem can be translated into saying that if you have a birational surface map or birational map on P2, if you compute the dynamical degree, it's either a PV number or a Salem number, which is quite striking. So there are many comments that you can make on this. So, yeah. So you can ask whether you can, for any iso or Salem number, that there exists a birational map, surface map for it. Lambda 1 is equal to this number. This is not exactly true. So I'm not going to discuss the whole story about this, but I'd like to mention this beautiful theorem by Blanc and Cantat. So you can look at the set of all dynamical degrees for any, let's say, element in the Cremona group, dimension 2. And so what they prove is that, so this is a subset of 1 plus infinity, and it consists only of PV number or Salem number. But in fact, you can show that this is a closed set, which is also well ordered. So in the sense that if you take any, in other words, any decreasing sequence is eventually stationary. Okay, so what this implies in particular is that you cannot find, so this is a real line, 0, 1, plus infinity. So if it is well ordered, it means that you cannot find a sequence of lambda 1 of f that can accumulate on the point 1, right? So in other words, you have a gap here. So there exists some epsilon positive, such that, let me give a name to this set, maybe capital lambda. So lambda intersected with the 1 excluded, 1 plus epsilon, is empty. So there are a lot of works on having more information about this. For instance, trying to describe the lambda 1 of f, for which f lived as an automorphism on some rational surface. So I'm not going to discuss all this, but they are beautiful papers. So if you want more references, I'm advising you to read this paper by Blanquentin or the book of Stéphane Lamy that contains this result. Am I right? Yeah. And so there are also beautiful results by Macmillan connected to this. Okay. Yeah. Yes. Yeah. Yeah. It's in my, in my first paper on this, where there are a lot of mistakes. I agree. But there is a nice family of degree 2 quadratic rational map. It's kind of nice because you can compute the dynamical degree completely, and you see that you have accumulation on the generic value of at the generic point on this family. Okay. So yeah, you can definitely accumulate. And in fact, it's a well-ordered set, so you have an associated ordinal, and I don't remember, I didn't check, but it's computable. It's what? Omega to the omega, right? I think. Yeah. Yeah. Someone else wanted to ask something? No? Yeah. Yeah. And it's true not only for P2, but for any surface. But the hard case is for P2, in fact. Okay, so let's try to prove which theorem? This one. So I'm not going to discuss this the other theorem because it relies on a deeper understanding of birational map and so on. So let me call this theorem 1. Okay, so remember this lemma that we had, which was saying that, so if I take, let's say, G, let me work only with birational maps. It's not really necessary, but two birational maps. Then if the degree of the composition, G composed with H, turns out to be strictly less than the product of the degrees, then something, a nice geometric fact is, this can be explained by a nice geometric fact. So this is supposedly P2, again P2, again P2. So here's H, here's G. And so if this happened, then this means that in fact you can find a curve, let's say C, which is contracted to a point by H, and then these points belong to the indeterminate set of G. So meaning what? Meaning that its total image has to be positive dimensional. So this is what I explained. Okay, so if the degree of Fn is equal to the degree of F to the n for all n, remember, most of the time it's like this, then, well, the theorem is not really a theorem. The lambda 1 is an integer, positive integer. And so there is nothing to prove. Otherwise, well, if you apply this lemma, well, you're in this kind of situation that you can find a curve that is contracted by F to a point, and then this point wanders around and eventually is blown up by F. So eventually fall into the indeterminacy locus of F. Okay? So this is when there exists, okay, let's say, I'll take the minimal n such that the degree of Fn is strictly less than degree of f to the n. And then here you have to take n iterates. Maybe this. So the first idea is to try to remove this this problem. And so the point is to blow up in the middle, so that this phenomenon of contraction followed by blowing up disappear, right? So first theorem. So there exists a sequence of blow up above P2. So let's say pi. Point blow-ups. Such that these things disappear, this problem disappear. Okay, so let me formulate this a little bit more. So let me call it a capital F, the lift of a small f to x. So what is this? Well, you have a point in x, so you have to push it down by pi to p2. Then you apply f by p minus 1. P is birational. So the first f is dynamically tamed. Okay, so I think that you heard the name. It's algebraically stable. So let me formalize this. Okay. So algebraically stable. By the way, this name is awful, but okay. So now it's has been written in the in the book. So I think it's yeah. We tried many times to change the terminology, but it was turned out to be impossible. Okay, so algebraically stable, it's dynamically well prepared if you want. Whoops. So what does it mean? So if you have a map, let's say it's from x to x, let's say x projective, smooth, and f birational. It also applies to any rational map, but here it's so is algebraically stable, or AS for short, if there exists no curve, no contracted curve. So curve contracted by f, such that that is eventually mapped to an intermediate point. So your map is algebraically stable if you don't see this phenomenon. Okay, so if you don't have a curve contracted to a point and mapped eventually to the intermediate locus. And the theorem tells you, well, maybe it's not algebraically stable in P2, no problem. If I blow up the indeterminacy point in the right order and so on, then eventually it will lift to an algebraically stable map. Okay, so I was lucky enough that apparently Christian also already proved this theorem. So for the proof, so you can look at exercise. So either following Christian approach or reading again Stefan's book. But the idea is really that for birational maps, any birational map on surfaces can be factored out as a sequence of blow-ups and blow-downs of points. And then the proof really follows from this structure theorem. Okay, so it means that if you see something contracted like this, then in fact, this process here is really the blow-up of that point, okay? And here it's the same. And so to resolve this, you just blow up in the middle, and then your bad curve just disappear. So I would say that it follows from Castelnuovo structure theorem. So let me insist on this, is that in fact this theorem is extremely specific to birational surface map. It completely collapses for any other kind of map. So it's not the theorem, let me call it 2 or 3, fails. So it fails for rational map, let's say non-invertible. And you have an easy example. If you take, for instance, the monomial map with A is equal to one of the two matrices that I choose last time, so 1, -2, 2, 1. And it also fails in higher dimension, so it fails for a birational map in dimension at least 3. And it fails really, really drastically, really badly. So you have, yeah, well, it fails. So, so you have a paper by Bell, Diller, Johnson, and Krieger. And what they did is that they exhibited an element of the criminal group of dimension 3, such that the dynamical degree is in fact transcendental. So I'm not explaining why, or I'm going to explain later, but this implies in particular, but in very strong form, that F cannot be algebraically stable in any model. In any blow-up of P3, but in fact in any on any rational variety. Okay? So we were very lucky to be able to prove this theorem at the time. Okay, so now let me explain how you exploit this existence of a rational surface above P2, over which F becomes algebraically stable, to infer my theorem 1, where is it? Here, that lambda 1 is an algebraic integer. Okay, so this is where the action of F on the cohomology plays a role. So, for the cohomology of rational surfaces is very easy to understand. And so, yeah. Sorry? Let me keep this on the board. Yeah, so here I need to look at the action of F on the cohomology H2 of X, which is the same as, since X is a rational surface, the same as the Picard group, which is the same as the Néron-Sévère space. And later on, I will work over an arbitrary projective variety, and so I'll focus more on the Néron-Sévère space. So let me, so here so want to explain that theorem, 2, or is it, yeah, 2, 3, sorry, implies theorem 1. And so this is where I need to explain how, so the lift is called capital F, the lift to X. So I need to explain how F acts on cohomology. Okay, so let me have like a small digression on the cohomology or Néron-Sévère space of X plus basic facts in intersection theory. So I know that Jeremy has also done most of the work, but just to put a couple of, to clarify things. So remember, so here X, let's say it's rational, it's smooth. projective surface. See? And later on, X will be a rational surface obtained by blowing up P2 at finitely many points. Okay. So the space of divisors, so this is a free abelian group generated by curves. So this is a set of formal sum like this, sum of AI, CI, or AI integral and CI are curves, not necessarily smooth. And so you have an intersection form. On this abelian group. So you're only here, by curve, I mean irreducible curve. So if C and D are irreducible curves, then the intersection product, one way to do that is that, so since you're on a smooth projective surface, D defines, it's a Cartier divisor, so it defines a line bundle. So let me write this as a sheaf, OXD. And you can look, so you can restrict this line bundle to the curve C and compute its degree. So this is an integer. Okay? And so it extends as a bilinear form. So you get a bilinear form from the set of divisor of X to Z. So now I'm going to be interested. So the set of all divisors is much too big. So I need to work with finite dimensional spaces. Okay. So it could be the cohomology, but here I'd like to work more algebraically, even though on rational surfaces it's the same. So let me define the neural subvariety space, NS. Whoops. So what is this? This is a quotient of the space of divisors by the numerical equivalence relation, so which is usually written but like this strange symbol, a 3 dash. So you say that the divisor Z1 is numerically equivalent to Z2 if and only if for any curve or for any C inside div of X, their intersection numbers agree. So Z1C is equal to Z2C. Okay, then the claim is that, in fact, this guy is finite dimensional. So instead of, so maybe later I'm going to do the same for a projective variety in any dimension. So maybe later I give more conceptual argument. But here, since we work with surfaces over P2 and we need some information about the intersection form on the neural subvariety space, I'll describe explicitly the neural subvariety space in that case. Again, probably Jeremy already did that, but okay, so what I want to do is so determine neural subvariety space of X when X is obtained by blowing up P2 at finitely many points. Okay, so one of the things, so I put NS of X, comma, these things. So here I'm interested also in the intersection form. So just a remark that so the intersection form descends to the quotient to NS of X. Okay. So how to do that is quite elementary because what you do is you start with P2. And here is not too difficult because the set of divisor up to linear equivalence is generated by O of 1. So it's, and so here you get Z times O of 1. So I don't like O of 1 usually. I put this like H, like the hyperplane. Okay, and the intersection form H to the square is plus 1, right? The intersection of two lines is 1. And so now, to understand the neural surface space of X, you only have to understand how, if you blow up a surface at one point, how the neural surface space is going to change. So this is what I'm going to explain. So suppose that pi is a blow up at one point from X to X prime, P inside X prime. And suppose you know what is neural surface space of X prime. I want to describe the neural surface space of X and also the intersection form. Okay? So if you know this, then you just apply recursively these things to the factorization of pi as a point blow-ups, and then you get the result. So okay. Here is the thing, is that, so you have the neural surface space. I want to compare the neural surface space of X prime versus the neural surface space of X. Okay, but so if you have, let's say, a Z, a divisor in X prime, then locally, Z is a Cartier divisor because my surface is smooth, and so is the divisor of pole and zeros of some function. Let me call it phi. Okay, and so you can define the pullback of Z at least locally by setting this as being the divisor of the pullback of phi, which is a composition of phi with pi. Okay, so this defines your morphism from the space of divisor of X prime to the space of divisor of X. And then there are some basic facts about the intersection of pullback of divisor that you need to know that I won't prove. But if you pull back, if you compute the intersection number of the pullback of two divisor, then in fact this is the intersection of Z1 with Z2. And also here, so pi, remember that this is a blow up at a point. And so you have an exceptional divisor, let's say E, which is the preimage of the point P. And well-known fact is that E squared is equal to -1. And also the pullback of any divisor respect to E is equal to 0. Okay, so I'm going to be a little bit fast here, but because of this, because pi is an isometry, in fact, it goes down to the quotient. So pi induce a linear map from the neural surface space of X prime to the neural surface space of X. Okay, and then you can check that this is injective. And in fact, what I'm going to explain is that the neural surface space of X, so let me identify, since it's injective, I can identify NS of X prime with its image inside this guy. So the neural surface space of X, you have this this image under pi star of NS of X prime, and what remains is what? Well, in fact, the class E. So it's you have to add the class generated by E. Okay? So how do you see this? Well, you take, let's say, you need to understand why any curve, maybe in X prime, can be written as a sum of the exceptional divisor plus someone that comes from where am I mixing up everything? Where is above? Above is X. Okay, sorry. So you take an irreducible curve in X. You have to say that this is the sum of the pullback of someone in X prime plus some constant times E. And again, this is what I think Jeremy explained. So if you pick C, a curve in X, then you can look at its image, let's say irreducible again. So here I'm trying to explain why the direct sum of these two things generate an X of X. So this is a class inside X prime. And then you can look at its pullback. But you see, so you have the curve here. So this is E, this is C, this is a point P, and this is pi of C. So if C intersect E, when you look at its image, it's probably going to have some singularity at P. And so when you pull it back this, what you get at the scheme theoretic level is you get C plus E. Okay? So then there are at the level of divisor, then you have some constants that have to come out. So what it means that this is equal to C plus some constant times E. And I think that Jeremy explained that this is in fact the multiplicity of this curve, pi of C at the point P. So I don't really care about this number, but at least this shows that any curve in X is in fact can be decomposed at the divisor, the pullback of the divisor in X prime plus some constant times the exceptional divisor. Okay, so it means it generates, and then why is it a direct sum? Well, you can look at the it follows from this identities. So this identity means that these two things are orthogonal for the intersection product. And so it has to be a direct sum. Okay, so when you iterate this, so remember that X was obtained by blowing up P2 at finitely many points. So you blow up maybe the point P1 and then P2, plop, 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 Pn. And so what you want to do is to exploit this to understand the neural survey space of X, right? So, okay, so neural survey space of P2 is, I said, is Z, H. So then I have to look at, okay, so in this factorization, I probably have to keep some names. So X is equal to Xn, goes down to Xn minus 1, up, X1, and this is X0, yeah. Okay, so the neural survey space of X1. Well, so by what preceded, so this Z times the blow up, the pullback by the blow up of my class H. Orthogonal sum Z, let's call it E1. E1 is the exceptional divisor. And then you continue, NS of X2. So I'm not going to do that for long, but this is a pullback by P2 of the pullback by P1 of H. Direct sum Z pullback by P2 of E1. Direct sum Z E2. And so on and so forth. So what you get at the end is that you have NS of Xn is Z times, well, the pullback by pi of my line bundle H down below, and then some other stuff. So Z, let me call it this E prime 1, E prime 2, maybe E hat 1, E hat 2, blah, 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 E hat N. Whoa. Okay, so what is the intersection form? So I already put this strange sign like there, so they're all orthogonal one to the other. But what is the intersection form of the self-intersection of this? Well, by the formula that I wrote somewhere here, box formula. Well, this is equal to H squared, so it's plus 1. And here it's the same. So remember, E hat 1, this is a pullback by the composition BLPN or BLP2 of E1. So here what you get is that E hat 1 square is E1 square is minus 1. And the same for all others, right? So minus 1, minus 1. Fantastic. So here, for if you're interested only in the Cremona group of in dimension 2, okay, probably it's you need to do all. Well, okay, fine. So you don't need to use deep theorems about intersection form on smooth rational surfaces. Here, X is obtained by blowing up finitely many points P2, and you get that the intersection form is of Lorentz type. So you have it's non-degenerate. It has one positive eigenvalues and all the others negative. Okay, so Lorentz type intersection form. So 1 plus and all minus, but it's even more because here have the integral structure of this space. Okay, so now I need to use. I want to use this to prove that the dynamical degree is an algebraic integer. So I see that time is flying, and since I need probably at least an hour and a half to explain the general definition of dynamical degrees, I might not have much time to prove this second part. Okay. We'll see. Okay, so I need to explain what is a pullback and push forward operator on ns of x. Okay, so let me suppose that x and let's say y and z are surfaces, smooth projective surfaces. And g birational. So I explain that there exists, so there is a pullback operator from the neural series space of z to the neural series space of y. And now what I would like to explain is that there are also a push-forward operator. So how is it defined? Okay. So if you take a curve, let's say reducible, inside y, you want to define the push-forward, let's say, as a divisor of, not of z, of c. And so then you have two cases. So here, when I'm saying a birational, it's a morphism. This is so either the image, so you can look at the image of C. So either it's a point, and then you set this to be 0, or it's not a point. It's equal to 1, and then what you do is you look at the divisor G of C, okay? And the claim is that, in fact, so this is a map at the level of divisors, okay? And the claim is that this push-forward operator descends to the non-series space of Z. I'm not sure to the necessary space of Y. Okay, so it's a bit confusing what I'm writing, so let me, okay, so this definition, so what I define let's say a group morphism of the set of divisors of Y to the set of divisor of Z. And then I like to check that if if C is a divisor in Y, such that C dot D is equal to 0 for all D. In other words, C is numerically trivial. then it implies that its image is also numerically trivial. And where does it come from? It comes from the fact that if you push forward your divisor C and you cup with D, then this is the same as C cup pulled back of D. So the definition of the push forward is done such that this identity is true. So if you want, G star, G lower star is transpose of G upper star. Okay? Okay, so let's come back. So now with all this, I can explain why lambda 1 is an algebraic integer when f is a birational map on the surface, on P2, let's say. So back to the proof of theorem 1. Okay, so remember, so F is a birational map from P2 to itself. And then we blow up P2 at finitely many points and found a rational surface, lift F to capital F, such that what? Such that so capital F is also birational, but is algebraically stable, plus algebraically stable. Okay, and so now I would like to, on P2, being algebraically stable means that the degree of Fn is the degree of F to the n, and so the key fact here is that F being algebraically stable is exactly the same as saying that it's equivalent to say that for any integer n, when you look at the action by pullback of Fn on the narrow survey space of X, then you have compatibility with iteration. So when I'm going to write it down, it's kind of subtle. So you can switch the star and n. So this is a pullback of n times. Okay? So you have compatibility between, if you want, when you're algebraically stable, you can read the action of all the iterates of F on the cohomology, on the narrow survey space, by just looking at one linear operator, this F star. You don't need to compute all of them. Okay, great. Maybe, so since time is flying, and I don't want to, So, exercise. Not really reasonable, but to say this, but yeah. So to understand this, in fact, well, okay, I can come back to this later, and the proof boils down to try to understand, just as the lemma degree of G composed with F is less than the product of degrees. So you're going to prove this not for the iterates of F, but you take two maps from, let's say, G and H, from surfaces to another one, and you want to compare the action on cohomology of the composition and each of them, okay? And so you need to construct a big diagram to understand all this, and at the end of the day, you get exactly what you want. But okay, so I'm going to write down this, to use this diagram later on, but I don't want to kill you right away. So let me continue and explain how, from this fact, this key fact, so when I say exercise, I'm not saying this is not, it's an observation. You have to be careful when you do the proof, but it's not super hard. No. No one disagree, I'm very happy. Okay, and okay, so let me show that lambda 1 is an algebraic integer. I didn't define F star. no, so this is, I'm a bad guy. Yeah. Of course, this is just before the key fact. Oops. Yeah, no, that's not reasonable. So let me define F star. Yeah, oops. I'm sorry. Yeah, I spent a lot of time defining the push forward and the pullback for morphism. And here it's a birational morphism, so it has point of intimacy. So how to define F star slash F lower star? We're going to need both, right? Yeah, well, my dash, yeah. It's really birational. Okay. Now, this is a crucial point, so let me spend some time on this. Thank you, Stefan. So remember that, so you have your birational map from X to X. And so remember that this is determined by, in fact, its graph, let's say gamma. But the graph is not necessarily smooth, so it's not very nice. So what I'm going to do is that I'm going to take any resolution of singularities of this graph. So just to say, not to confuse with the notation I had before, let me denote this by gamma hat. So in other words, here you're working with a birational surface map. So this diagram here, where you have f, pi 1, and pi 2, can also be obtained by Castelnuovo theorem. So pi 1 and pi 2, so first gamma hat is projective, smooth space, and pi 1 and pi 2 are birational. Okay, and so you want to define the pullback at the level of narrow surface space. So what I explained is that I know how to pull back when it is a morphism. So I can always pull back a class, a divisor class in X to gamma hat. And I explained that I can also push forward. Okay, so it's kind of natural to define the pullback of F as the pullback by pi 2 composed with the push forward by pi 1. And so this is going to be a morphism on narrow surface space to itself. And if you want to define the push forward, well, okay, you can always say that F is invertible, so you pull back its inverse, but otherwise, it's also the pullback by pi 1 and then the push forward by pi 2. Okay? Yeah, it's kind of essential. And so what I was saying is that, so in general, when you iterate n times and you look at the pullback on the narrow surface space, as it's not equal to the pullback, the nth iterate of the pullback. But when you're algebraically stable, then you exactly get this fact. So let me deduce from this that lambda 1 is an algebraic integer. Hello. Where are you? Yeah. Okay, so consequence. Lambda 1 of f okay, so what is the observation is that, so when you look how you compute the degrees in terms of the action on cohomology, so remember that the narrow surface space of P2 is generated by a line, and so if you pull back a line, then you get the degree of f times a line, the class of a line. Okay? And so in particular, if you pull it back n times, so I'm just curious, now maybe I use H and not L, sorry. Oops. So this is in P2. And so if you pull back this line or this hyperplane n times, you get the degree of Fn times h. Okay, good. So now you have this commutative diagram that I probably erased. So you have, let me write this way. So you have f, x, pi 2, oops, pi. This is p2, f, p2. And this is... Okay, so what I'm going to write is, so what I'm doing here is that I have this h here. I can pull it back by Fn, and I get the degree by like this, right? So now what I can do also is, instead of doing this, I can look at pull back by pi, pull back by Fn, and then push forward by pi, okay? And what I'm going to claim is that this is a way to relate this degree to the action of Fn on the cohomology. Okay, so I have to be a bit careful. So Fn, it's a composition of what? Pi minus 1 composed with f, capital F to the n, composed with pi. And now I'm taking pullbacks. And now I'm realizing that the proof of the key fact uses something I need here, of course. Yeah, well done. Okay. Okay. So what I'm going to do is I'm going to apply Fn star to H, and I'm going to compute this. And so let me do this formally, okay? So here, I need to justify this a little bit. But what I'm going to say is that in this situation, in this very specific situation, in fact, I can switch the composition of the pullbacks. So what this says is that, in fact, this is pi upper star composed with Fn upper star composed with pi minus 1 upper star, which is pi lower star. So I'll explain this a little bit later. Now, you look. So now you compute this on H. So you know that this is a degree of Fn times H. And what is this? This is pi lower star of pullback of this class. And here I'm going to use the fact that F is algebraically stable. So this is F star to the n composed with this. Okay? Okay, so you have a nice equality here in terms of classes. And so one way to get some numbers is to intersect with H. So when I intersect this equality with H, on the left-hand side, I get the degree of Fn, because the intersection, self-intersection of line is +1. And on the other side, I get H intersected with push forward, pull back by F to the n, pull back H. And so here I'm using the fact that the push forward, the pullback is the transpose of the push forward. And so this is pullback of H, composed F's upper star and pullback of H. And my writing is decaying. Okay? If this is possible. Okay, good. So it's kind of nice, because what you see is this. So pi upper star of H is an element in your neural series space. So pi upper star H. This is some class alpha, the neural series space of X. And you have an intersection form on the neural series space, which is integral. And the map F star is also integral. It's an integral matrix inside the neural series space. So here, remember, this is the n. So if you want f, whoops, not n, maybe L. So f upper star can be identified with a matrix, square matrix, with integral coefficients. And here, what you're looking at, what you prove, is the degree of Fn is in fact the intersection form of this class alpha with the pullback of this with alpha. Okay? Okay, fine. So what's going to happen is that when you look at the degree of Fn to the power 1 over n, this has to tend to converge to some eigenvalue of f upper star. Okay, so this is basic, let's say, linear algebra. But your matrix here, f star, is in fact with integral coefficients, and so they are all algebraic integers. So it doesn't say anything about the Galois conjugates and so on. You need a little bit more, okay? But at least just because of the fact that f is algebraically stable, and you can interpret this f, it's, where is it? Here. And the pullback of Fn is, in fact, the pullback of Fn is equal to the nth iterate of the pullback of f. Then you relate the degrees to the action of just one matrix, and you prove that this limit is in fact just one eigenvalue of the action of f. Okay, so we already seen something like this, right? When we computed the dynamical degree of a monomial map. Of course, in the case of monomial map, you directly have some matrix, so it's not. And so we also interpreted the dynamical degree as an eigenvalue of some matrix with integral coefficients. Okay, so let me spend like a couple of minutes to discuss these things. Here I was not very careful. Yep. And then what? Yeah, then I have to think a little bit about the organization of the rest of the lecture. Okay, so this comes from the proof of the key facts. So let me discuss a little bit more this key fact. And so what you actually prove is something like this. So you have x, you have a map to y, let me call it g, and then you have another map to z. So let me assume that x, y, z are rational surfaces or smooth projective surfaces, and g and h are birational, even though the fact being birational is not essential. And so if I have two maps like this, I have a pullback operator from narrow series space of z to the one of y, and the pullback operator for narrow series space of y to the one of x. And so I can do two things. So I can look at the composition of these two maps, h composed with g, pullback. So this is a map from narrow series space of z to the one of x. But I can also look at the composition of the two operator here, okay? And the claim is that h composed with g upper star is equal, or is equal to g star composed with h star, if and only if you have the same phenomenon as I explained in P2. So there is no curve, let's say reducible, C, that is contracted by G, so such that its proper image by G is a point, which is blown up by H. So it's a point inside the indeterminate locus of H. Okay, so this is a key of these things. So if you're able to understand, if you do the exercise and prove this lemma, then you apply this lemma as I did for the projective space to iterates of suitable iterates of f, and then you show exactly this this key fact. Okay, so let me now comment why this is this implies this equality here. So we're going to apply the lemma, let's say twice. So you want to here you have a composition, not only 2 maps but 3 maps, right? So f a priori is bad, it can contract things. But here you're composing with pi minus 1. So you go from P2 to X. You're blowing up things. So you don't contract anything, okay? So the composition of pi minus 1 with anything satisfies this, this lemma. And so you can take this out, okay? So pi fn, pi minus 1 upper star, this is pi upper star composed with this guy upper star. And then you look at the second step here. And now the point is that pi is regular. So since pi is regular, it has no point indeterminacy. So again, you can apply this lemma, okay? And so again, so now you get exactly this, this formula. Okay? Okay, yeah. So I think, how much time do you have? 20 minutes. Yeah, blah, blah, blah. Okay, so the plan was to explain now how you get the second part of the theorem, the fact that the Galois conjugates are inside the unit disk. Let me give a brief idea in the case that F is an automorphism. And then I comment in the general case, and then I'll try to start the general theory. Okay, so goal. So we know that lambda 1, so all conjugates of lambda 1 lie in the closed unit disk. So let me give some idea about this. Yeah, okay, so we're going to work now. So I'm going to replace, I'm going to work all the time with capital F and look at the action on the inner Fourier space, because I know that I can read off lambda 1 from the spectral properties of capital F. Okay? So, and again, so what I know is that the pullback is a transpose of the push forward. And so since the intersection form is perfect, then it means that the spectrum, so what is the spectrum? This is a set of all eigenvalues. So the spectrum of the pullback is the same as the spectrum of the push forward. So now the claim is that, so if you want to understand a little bit more the Galois conjugates of lambda 1, you need to understand how the pullback of F interacts with the intersection form. And when F is an automorphism, which happens sometimes, then it's quite clear that in this case, in fact, the pullback is an isometry of this intersection form. And so you have a very nice interaction with the with the intersection form. When F is only birational, which is capital F here, it's interesting. So this formula cannot be true, but in fact you have a good control on the difference between the two. So I'm not going to prove it. Again, exercise. But in fact, what you can show is that you can understand what is the defect of F star to be an isometry. And so the pullback of the intersection of the pullback of alpha with the pullback of beta is the intersection of alpha and beta plus some extra stuff. plus, so let me write it down. So the claim is that there exist some effective divisors, VI. So these effective divisors are supported on the image by F, well, capital F, of point of indeterminacy. And what is the good point in this formula is that it says that the pullback preserves the form up to this, and this is also a quadratic form, but which is non-negative, right? If you put alpha is equal to beta, here you have a sum of squares, vi the alpha to the square. So here, when f is birational, maybe you don't have equality, but you have to think that, in fact, the pullback is greater or equal to this, okay? And this forces these things implies exactly what we want, that all the conjugate lies in the unit disk. So I'm not going to do the exercise in the case of birational map, but let's do it very quickly on for automorphisms. So what you're going to see next week, I hope you didn't see yet, but is that in fact F not only acts on the nursery space of one model, but on the nursery space of all models, of the bubble space if you want. And then at the level of the bubble space, this disappears. Because when you're blowing up all points, somehow the intuition, the heuristic is saying that in fact you have killed all the indeterminacy of F. So in this infinite dimensional space, then in fact now the pullback is going to be an isometry. Okay, but here is I force you to think at the finite dimensional level, and so then this in the birational case there is some interaction with the indeterminacy locus. Okay, whatever. So yeah, let me assume that F is an automorphism of X. So you have examples like this, right? So if you blow up at least 10 points in a special position, that sometimes F leads to an automorphism. So it's not, what I'm going to prove here is not an empty statement. Okay, so let me assume that lambda is greater than 1, otherwise there's nothing to do. And yeah, so I know that there exists a class. So I know that lambda 1 is an eigenvalue, it's in the spectrum. And so there exists a class alpha, which is whose pullback, here it's capital F, sorry. So there exists an eigenvector alpha attached to lambda 1. Okay, so now let me compute f alpha to the square. So this is lambda 1 square alpha to the square. But here what I said is that I have an automorphism, and so this is an isometry from the intersection form, so this is alpha to the square. And since lambda 1 is different from 1, is greater than 1, then this implies that the self-intersection of alpha has to be 0. Okay, so now you play this game. So, okay, let me assume now that mu is an eigenvalue, and also that its norm, it has at least 1. So just don't want to play with complex numbers, too complicated. Let me assume that, in fact, mu is real, greater than 1. I want to show that this is not really possible, except if mu is equal to lambda 1. Okay, so pick an eigenvector attached to beta, and you play the same game. So the same game tells you that beta to the square is equal to 0. But you can also look at the intersection of alpha and beta, right? So this is alpha dot beta, because in the isometry. But here, alpha is the eigenvector for with the eigenvalue lambda 1, and beta is the eigenvector with eigenvalue mu. So this is also lambda 1 times mu alpha beta. Okay, so here, in fact, I get, yeah, well, Okay, so this implies what? This implies again that alpha dot beta is equal to 0. Yeah. And so now my intersection form here is non. I was thinking I need to use Lorentz type, but just for this argument, is my intersection form is non-degenerate, so it implies that beta has to be parallel to alpha. Okay. So in this way, you show that you show that all eigenvalues have to be inside the closed unit disk. In fact, you show a little bit more, so you can push this argument. Let me just write here what you can do with this kind of argument and playing around with the fact that the intersection form is of Lorentzian type. Now, I said I didn't really use Hodge, I think. But yeah. No? Did I? I conclude that mu, if mu is greater than 1, it has to be equal to lambda 1. I use the fact that it is, yeah, well, it is, I use the fact that it is non-degenerate because then the intersection is completely 0 on the plane, which is not possible. I know, but yeah, okay, sorry, yeah. Sure. Yeah, okay, so let me, yeah. Okay, so let me finish the thing. So, okay, if, whoops. So if, yeah, sorry. So if mu is not equal to lambda 1, then in fact the intersection form, the restriction of the intersection form on, let's say, a vector space generated by alpha and beta is identically 0, but my intersection form is, has 1 plus and only minuses, and so this is impossible. You cannot find a plane over which the form is identically 0. Okay, so this implies that the spectrum of the pullback of F, if you remove lambda 1, this is inside the closed unit disk. Okay, so in fact, the last comment I would like to make is that in fact, lambda 1 is a simple eigenvalue. For F star. Okay, and so if you know that, so it's exactly the same, same kind of argument. But if you know that, then this implies something about the growth of degrees, for instance. So if you use this, then it means that the growth of the degrees, in fact, you can show that this is, at least if lambda 1 is at least 1, then this is lambda 1 to the n plus big O of 1. And here I'm a bit tired, I'm going to say a lot of stupid things, so let me put some positive constants, but maybe the constant is 1, I don't remember. Okay, and so just to make some commercial, it's so with backdown, we partially generalize this kind of result to higher dimensions. Okay, so yeah, it's not completely satisfactory. I didn't prove the key lemma, and I didn't explain how from this boxed equation you get exactly the same kind of result. But since I've already used this name, like given as an exercise, I'm not going to spend too much time on this. Okay, so now, yeah, so now let's go. So what time is it? 9 minutes. Whoa, so precise. Yeah. So yeah, let me stop discussing the birational case and try to start giving an overview of the general theory. So what I want now is stop looking at specific example. Is okay, so I'm taking X, a smooth projective manifold, so variety over C of dimension D. I'm going to consider F a rational dominant map. And I want to define dynamical degrees. So these numbers, lambda 1 of F, lambda 2 of F, blah, 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 lambda D of F. So there are two ways of, we need to generalize this in two ways. So first, I replace the projective space by some arbitrary smooth projective variety. And then also, I want to define all these other intermediate degrees. So we saw that, so here, there should be a lambda 0, right? But lambda 0, I won't talk much about this. This is always equal to 1 for maps. And this one, so this one, we saw it on the projective space. And here, this one is in fact, so we saw it also for rational surfaces, is the topological degree. So in the remaining 9 minus 2 minutes, yeah, what do I want to do? I want to probably try to define the degrees. So yeah, great. Yeah, I'm going to spend like 8 minutes to think about what I need to do in the remaining 8 minutes. Okay. Let me write down a couple of things and try to have explain the roadmap for the last hour. Okay. I didn't manage very well this timing. Okay, so this lambda k of F, they are going to be defined also so as the limit of degrees of the iterates. Okay? So the thing is that I need to define what is the degree, the case degree of a rational map. In the case of a general smooth projective variety. And so to do that, you need to make some choices. So we need to choose some ample line bundle. So remember, an ample line bundle is a line bundle for which, if you look at some huge power of L, and you look at so it has no section or no base point, and the morphism from X to the projectivization of the dual of the space of section gives you an embedding into some projective space. Okay, so in other words, X is sits inside some Pn, and L is in fact O of 1 restricted to X. This means a very ample, but whatever. Okay, and then what we need to define, so we need to use this line bundle to define a degree, and the degree is going to be defined using intersection product. So let me write down a couple of things, and then I'll try to explain this afternoon if you are still alive. So okay, so if I have a line bundle, I can look at its first chain class, so which is an element in the Durham cohomology of X with real coefficient, if you want. And so here, what you do is you look at the first chain class, and you capitate it k times with itself. So this is some class now which lies in H2k Durham of X. And just as before, I'm going to pull it back by F, and then cup it with the thing such that you get a number. So here you have to look at C1 to the L and probably D minus K. Okay, and so this is going to be, so I need to explain that this is a positive integer. And so when you do this, there are many issues. So one of the issue, of course, is that f is rational. And so if you want to pull back classes when f is rational, this is not quite clear what this means. And so I'm going to use the same trick as before. So I'm going to look at interpret f by looking at this graph. So now I know that pi1 is only birational. Pi2 is, since it's dominant, it's just generically finite. And again, gamma is singular, so it's not a good thing to do, especially if you want to intersect divisors. And so I'm going to replace this diagram by gamma hat, which is a resolution of singularities of gamma. Not really essential, but okay. And so what is these things? Well, the pullback of a Durham class, okay, it's going to be as before. So you know that a Durham class inside X, since pi2 is a morphism, gamma hat is smooth, you can always pull it back. Okay, you have a form, smooth form, you pull it back, you get a smooth form. So this is fine. Now the second thing is a priori a bit more delicate. Now you want to push it down to X. So pushing down forms is not really nice, except that here pi1 is birational. So when you push down a smooth form, it's smooth almost everywhere, away from the image under pi1 of the exceptional locus. In fact, you can check that this is always a form with L1 coefficients. But one way to define this push forward at the level of a cohomology is if you're knowledgeable, you can also, so this is something I already used. The Durham cohomology is also the set of, let's say, current in gamma hat, closed current in gamma hat, modulo exact ones. And current, since everyone is, it's projective, pi1 is proper, and so you can push forward current. So pi1 star is can be let's say is well defined at the level of currents and commutes with the differential, and so descends to the Durham cohomology. So here I'm looking at 2K degree 2K. Okay. And probably I have to stop. So this afternoon I'm going to be a bit more precise about this and try to prove that this limit exists, and so try to prove that the degrees are submultiplicative. It's not exactly submultiplicative, but it's up to a constant. Okay, so I'll try to explain this. Yeah. Thank you.
Yeah, thank you very much. Are there any questions? Yeah.
So I want to ask about the algebraic stable, and you mean if f is algebraic stable, then f pullback n alpha intersect alpha equals to fn pullback alpha intersect alpha. But the converse is not true. So can we consider something about the numerical stable like that? And is there any result about this?
I'm not sure I understood the thing. So what? It's I don't think I understood the question, I'm sorry. So I think algebraic stability, at least for surfaces, this is equivalent to what I wrote. No?
But for example, higher dimensional or some rational maps, the converse is
Yeah,
not
yeah,
true.
okay. So, yeah, this notion of algebraic stability, it works very well for birational surface map, okay? Also for rational map in dimension 2. In higher dimension, you have some conditions on the contracted set in its image. If it's of low dimension, then the action on cohomology is going to be good also, but you don't have the equivalence. This is what you're asking?
I mean, yeah, if we want to compute dynamic degree, we just need the intersection numbers.
Yeah, that's true. Yeah.
So we just need F pullback R. We just need to find a big ample Lambda R such as F pullback N R intersect alpha equals to the F N pullback alpha intersect alpha. So
yeah.
So it's weaker than algebraically stable.
Yeah, true. Yeah, yeah.
Is there any result about this?
For example, but you ask. I'm sorry. I'm a bit tired, but I'm not understanding exactly what you mean. It says, yeah, you. Are you asking that are there some geometric conditions enforcing the fact that you have commutation between action and pullbacks and iteration? The answer is yes. And then, do we have like general results saying that for this map we can make it what they like K stable or things? Outside this, I don't think so, or maybe automorphism of polynomial maps of C2, and that's it.
Okay.
And maybe a little bit more of affine surfaces, but outside this, there's nothing.
Okay.
Dimension. I think my point of view is that in higher dimension, this is a much too strong assumption. Okay. If you're lucky, if you have fixed maps, and then you can check whether you can find some models like this, and check that it's the action is good. But otherwise, for general theory, I think it's not the right direction. Okay. I'm sorry if fair enough.
Further questions? Yeah.
Okay, yeah. So I think you like at the very start, like you mentioned that the algebraic stability may be like changed with some better word. Like, what's your suggestion? Algebraic stability.
Yeah. Yeah.
Yeah. Okay. Alternative terminology for algebraic stability that you had in mind.
Yeah. So one stable. What is this? I'm not sure why people are calling this stable.
Okay.
I don't think it's dynamically well prepared. Is probably better, but now it's in a fantastic book by Stefan. So algebraic stability is going to be for the next millennium. Yeah, sure. It's always like this with my kids, and it's my fault, you know.
Sounds like a long and complicated history. Yeah.
No, but it turns out that this, so at the very long ago, we thought that this notion was really essential. Maybe it's not that. No? At least you need if you want just to compute dynamical degrees, you can have much weaker form of algebraic stability.